So hi, I'm Aditi, and I'm going to talk today about introducing Prestissimo, Presto's next-gen query execution engine. So this is the first talk among many today on Prestissimo. And this talk is actually a very generic introduction to Prestissimo, the motivation for the project, the architecture, giving some understanding of the concepts in Prestissimo, and then I'll sort of cover project status from a community perspective, and give more information about the different channels in the community and how to contact us and all that. There are subsequent sessions from Meta and ByteDance, mainly today, that will give more specific results with Prestissimo on their query workloads. I don't have like any fancy benchmark numbers or anything to present here. The talk today, I'll talk about the motivation for Prestissimo, and that will be followed by a deep dive into the Prestissimo architecture and the Velox concept. So Prestissimo is built off a library called Velox, and I'll explain some of the underlying building blocks in Velox. At the end, I'll talk about the project status, where we are, and some of the new initiatives that we are going to work on in the next few years, and the community. So what is Prestissimo? So Prestissimo is a full rewrite of the Presto query eval, and this is called the Presto worker in the cluster architecture today. So if you want to think about it very simplistically, what is done is you take the Presto cluster today and replace all the Presto Java processes with equivalent native C++ worker processes. The rest of the cluster just continues to work as it has before. So native execution, right, it's very much a state-of-the-art thing. There are multiple industry initiatives out there, most notably like Photon from Databricks, that are looking at native execution engine for query eval. And so Prestissimo is kind of a project in a similar theme. There are similarities, differences, different trade-offs. We're all very excited to bring all these state-of-the-art developments to the Presto world. So pictorially depicting what the project is doing, right? This is what a Presto cluster looks like today. So you have one or more coordinator nodes, and then you have several workers. I mean, we're talking to the tune of hundreds of workers in the Presto cluster. And usually you have a Hive meta store that has metadata about the tables that you're kind of going to work on. So the client comes in, connects to the coordinator, and the SQL query is submit at the coordinator. The coordinator, usually in tandem with a Hive meta store, parses and optimizes this query into a physical execution plan. Now, this physical execution plan is what is going to be executed on the workers. When you think of the physical execution plan, because this is like a distributed cluster, your physical plan could comprise of multiple stages, each stage like doing like one step of the query processing typically. And these stages are actually executed at the workers. So now every stage manifests as what's called a task on the worker, and every task has the part of the plan fragment, the plan nodes corresponding to the plan fragment that are actually going to be processed to get the query results. So the optimizer comes up with this physical execution plan, and then you have the scheduler that takes the stages and tasks corresponding to the query plan and schedules all of them on the workers. So the workers kind of operate on each task independently. Now, because you have big data, your data is split across multiple partitions, and the workers work on individual partitions. So the scheduler, in addition to scheduling the tasks, also looks at what are called splits of the table, and it gets the splits from the Hive meta store, and then it starts scheduling splits to individual workers. And all this puts in place what starts the next phase, which is the actual data movement. So now when the worker receives these splits, it could read data via table scan nodes in the plan. And your data is typically on object stores like S3, HDFS, and the data could be in Oracle Parquet files. That's what we support to a large degree. And the workers read data into the eval engine. Based on the query plan that you have, you could do like subsequent transformations. These could be like expressions, aggregations, joins, and the worker does all the query processing for these different plan nodes and generates data which could be the input for the subsequent stages. So it's possible that your worker then redistributes the data via exchanges for the next stage. And eventually you reach the final stage of the query processing, which computes the final results and returns them to the user. So this is, in a nutshell, what happens when a query executes in Presto. And today, all these pieces, the coordinator, worker, everything is written in Java. And Java, the technology, the language, the infrastructure keeps evolving. But like it inherently comes with limitations because of the JVM interpretation, GC pauses, and of course there's a whole party of engineers who work on native runtimes, and to them all this can seem a bit limiting, and you know, I mean they can just do much more with performance at every level in the stack with C++. So what Prestissimo does is you kind of work with the same cluster architecture as before, but the pink Java Presto worker boxes are replaced with Prestissimo workers instead. And so like the control API, all aspects of the control API between the coordinator and the workers remain the same, but you have a different runtime that processes data differently. So the rest of the system to the user kind of looks the same. Your user still submits the query at the coordinator, and you know, all the parsing, optimizing, scheduling is as before, but the runtime is just different. So the C++ worker, so you will constantly hear about Prestissimo and Velox. Prestissimo is the C++ Presto worker, and the Prestissimo code is written over the Velox library. Velox as a library is a library of data processing primitives that leverage the latest developments in like vectorization, SIMD, a lot of advanced runtime optimizations. Velox also comes with an async data cache that has features for smart I/O, prefetching, caching, and Velox has a homegrown memory management system with sophisticated features like memory arbitration. Now, this is all a mouthful, and in subsequent slides, I will actually kind of explain these concepts with an example. As I mentioned before, Prestissimo is built on Velox. And to give some background about Velox, actually Pedro here, who's the project leader for Velox, has written this paper, Velox Meta's Unified Execution Engine, which has a lot of details about the project, and it was presented at VLDB last year. So that has as many details as you want, but to kind of explain, to give a summary of what happened is, right, that the data infrastructure team at Meta kind of realized that engineers typically used multiple like query evals for different data processing tasks. So you had Presto, Spark, Presto and Spark, streaming and other ML pipelines at Meta. And each one of these had their own runtimes, even multiple native runtimes. And all these engines typically, like they kind of had similar abstractions for the query processing, and you know, many of the algorithms are also very similar. And but there was all this repetition and customization across different engines. So the initiative was to consolidate all this knowledge into one library, that's Velox. And so Velox kind of provided the data processing primitives that are now available to all the engines to use. And of course, like this also has the advantages that Naveen mentioned, right? That you can have a single SQL and it's kind of operational across multiple query engines because because of this underlying technology. And like there are many benefits because now all the engineers learn one ecosystem and understand it very deeply. So, so what does Velox give you? It's a library of data processing primitives. A lot of the algorithms are based on vectorization, SIMD, adaptive runtime optimizations. Since this is a native engine, it also has a homegrown memory management system with sophisticated features. So what was the benefit of doing all this, right? Price performance, pretty much, that just captures everything. There will be more results that are given, and I mean, there were some results in the morning as well. But what we see now is that we can perform the same query workload with much smaller clusters. And we've typically seen like the number of nodes in the cluster. I mean, we can do the same query processing with like a cluster that's half the size. And there's some groups that got even more aggressive because they wanted to see how far this can go. And they've even seen success with like clusters 1/3 of the size. Prestissimo has a very good price performance story. Since the system doesn't have any Java or JVM garbage collection, performance cliffs that kind of were observed in the past are not there anymore. Because of C++ native execution, all the memory management, SIMD, is under explicit control. And so like we have, performance is better understood. We have a whole lot of runtime counters that engineers can look at to analyze the system performance and come up with more optimizations. And and because of Velox, you have a single set of reusable and extensible primitives used across multiple data engines. And so this kind of also brings in a whole lot of engineering efficiency, if you will, into play. And so we have seen a lot of benefits of Velox and Prestissimo over the last few years. So we started working on this like maybe 2-3 years ago now. And in this last year, we've actually seen many of these, the benefits of many of these things play out. So we're all very excited about this project and can't wait to see what happens in the next 2-3 years as well. So the next part of the presentation actually kind of tries to explain some of the concepts in the query processing with an example. So the example I have here is I've picked up a modified TPCH Q1 query. And so what this query does is it's a simple table scan of the line item table in the TPCH schema. And the table scan is bounded by a predicate on ship date column. So the results of the table scan are then, so we compute a hash aggregation on the results. We group the data by return flag line status to compute certain aggregations. So we have a bunch of aggregations that are computed, the count of orders, the quantities, the sum quantity, and the discounted price. And these results are then globally sorted by return flag line status and returned to the user. So this is a very like simple query that we want to execute. And if you look at it, the logical plan is what kind of looks, is represented on the right-hand side. So at the logical level in the coordinator, we kind of determine that we want to execute this with what is called a scan filter project of the line item. That plan node feeds into hash aggregation that will group by the return flag and line status columns. It will compute all the aggregations that we want. And then this result will feed into a global sort that will sort by the return flag and line status columns. Now, this is what it is at a logical level. But in order to execute this on the cluster, we transform this into a physical execution plan. So like I mentioned before, the physical execution plan does data processing in stages, and each stage is scheduled on all the workers in parallel at the same time. So The previous example query kind of gets planned into a physical execution plan that has like 4 stages. Like the operators in the stage like roughly correspond to the same plan nodes, but it's again roughly. There are many optimizations that could combine processing depending on like what the optimizer decides. So the previous query gets transformed into this physical execution plan, which has 4 stages. And like the logical plan, if you look at it bottom up, the processing starts at the bottom. You have a scan filter project of the line, a table node that kind of reads the line item table. And the predicate that you see, it can be pushed down to the table scan. The results of this feed in within the same stage into a partial ag. So like the previous hash aggregation is now split in 2 parts. You have a partial aggregation that happens at the lower stage. And the results feed into the next stage where we do a final aggregation. The results of the final aggregation are then fed to the next stage where there's a partial sort and local merge. And the results of this final stage, this stage are sent to the client via an output operator. So each of these stages need to be executed at the worker, and the manifestation of each stage at a worker is called a task. So eventually what the worker is going to see is going to be like this infinite loop where it keeps receiving task requests. Each task request has a plan fragment, and the plan fragment has the schema of all the nodes that are needed for the query processing for that task. And the Prestissimo is basically just an infinite loop that keeps receiving task requests, does all the data processing for the task, and returns results to the user. So what happens in the native execution today is that this Prestissimo control loop is the same control loop that was in the Presto Java worker as well. But Prestissimo receives the Presto plan fragment with the Presto plan nodes, and it converts this into a Velox plan with Velox plan nodes. The Prestissimo shim kind of sets up the thread pool and IO executors and remote exchanges. And at this point, we completely move to like Velox processing. So Prestissimo hands this over to what is called a Velox driver component. And that actually does the data movement that's needed for the query processing. So the Velox plan node, at this point, like now we've kind of completely moved to the Velox world. So in Velox, you have the API comprises all these plan nodes, and as you can see, we have a variety of plan nodes that are implemented in Velox today. So in the previous query, we would end up using the plan nodes that are highlighted. So the table scan node in one stage, the aggregation node, which could be a partial or a final aggregation. And then we also going to use the order by node in the last stage. In addition to these nodes, right, we have join nodes, we have limit, unnest, window. The query processing that happens in Velox today is fairly rich. So the plan node is just a spec of like the query processing that you want to do. But the actual data movement happens in operators. So what Velox does is it compiles down the plan fragment that it might have received into a pipeline of operators. And when the operators receive data, and this may be via a split or via exchange, the operators start doing the data transformations that are needed and move the data along through the execution pipeline. So basically, like this diagram kind of zooms in at every level of the processing. So like you have the stage execution plan. Each stage consists of multiple tasks on the workers. And if you zoom into a task, you will see that the task had a plan fragment. And that plan fragment actually comprised multiple plan nodes. And even each of these plan fragments, right, there are many parts of it that can be executed in parallel at each worker. And so you have the Velox driver that kind of goes in there. So in this slide, we see what's happening with the final aggregation, right? So the Velox driver figures that it's going to do this with 3 independent pipelines. And so we kind of duplicate the plan fragment comprising the aggregation and the output in 3 pipelines. And then when this task begins receiving data at the remote source, It'll multiplex our data via the local exchange into these 3 independent pipelines. And then the Velox operators will transform the data it receives and send this on the output exchange to the subsequent task. So that's what happens in the system. If you hear subsequent talks, like many of them will talk about like individual operators and how the query performance was increased by tweaking different parameters of these operators. I hope this slide kind of gives context to the architecture there. So I want to talk a bit more about the concepts in Velox. So the Velox runtime comprises of all those operators, but the main principles underlying it are vectorization. And so all the data flowing in Velox is represented with vectors. So vectors, I mean, so typical so data processing could be like row oriented, but the most efficiency increases are when you represent your data with column based vectors. And because we are looking at a column of vectors at a time, we could like capture data about the data to build what are called encodings. And so if you see that you have only constant data, you can build a constant vector, you could have flat vectors or scalar data, you could have dictionaries. And so Velox, all Velox processing happens using these vector primitives. The vectors are allocated using a memory allocator, and the memory allocations are tracked in what is called a memory pool. And the memory pools have allocations tracked at the operator level, and they kind of add in to a task level memory pool. The buffer management, the memory allocator buffer management algorithm is inspired by the Umbra hyper design, and this is like pretty much state of the art buffer pool management work. So I mentioned adaptive runtime optimizations a couple of times, and what does that mean? So like I mentioned before, right, so vectors can capture data about data. And when we have that, we can do many more optimizations based on what we know. So for example, we can capture if your data has nulls, we can capture the positions that are null. We can capture if like your string column is all ASCII, we can capture what are the number of distinct values in your column data. And based on this, you can actually, at runtime, flip your execution algorithm to something more efficient. So like if you know your data doesn't have nulls, you choose a fast path which doesn't do any null checks. If you have all ASCII data, you choose all ASCII fast paths. Your table scan could reorder column reading based on knowledge of the selectivity of each predicate. The hash table knows about the number of distinct values, and so it can choose a hash strategy based on the most efficient algorithm for that, for the number of values that we're seeing. So if you look at Velox code, there's a lot of interesting stuff done around adaptive runtime optimizations, and that's a fairly cornerstone principle in Velox. And the last thing I want to talk about is memory arbitration, and this is something fancy that has happened in the last year or so. And what memory arbitration gives you is you can really improve memory efficiency, especially for queries on big data, long-running queries. The memory arbitration feature, basically what it lets you do is you can pause execution of a lower priority query, reclaim memory from it, and then move this memory around to another query, to another high priority query, and let that be completed before the lower priority one. So this is achieved with a framework called spilling. And in the last year, there's been a lot of work done in spilling and memory arbitration, and we are now able to run bigger queries than we were ever able to in the past. And so this is some exciting work in progress. So I hope that gives a lot of information about Prestissimo, Velox, and the concepts underlying it. In terms of where we are with the project, so we kind of started working on this project like 2 or 3 years ago. And the main focus these years was to kind of get a good SQL coverage and show like really good numbers and performance benchmarks. And so at a community perspective, we kind of focused on the TBCH and TBCDS benchmarks. And we had to implement a lot of features to make these happen. And as of last month, we have been able to run these benchmarks to a scale of 10 terabyte. And we are seeing really good numbers. I think Satya had some stuff to share, numbers to share earlier. In order to achieve the TBCH and TBCDS queries, we had to implement a lot of features. The TBCH has a lot of correlated joins. DS has window functions, grouping sets, decimals. In the last 2 years, we've also started supporting table writes, DML. You can do a CTAS with Prestissimo today. In terms of the object stores supported, we support S3, HDFS, and GCS storage systems. And one of the big projects was also this highly performant Parquet reader. We also have Parquet writing now. This has very good optimizations for predicate pushdown and the like. And that's one of the components that's contributed to like all the great numbers that we have. From a system administration perspective, the async data cache is also available, and spilling support is available now. In terms of what we want to do in the future, we have a lot of like SQL coverage now, but I kind of glossed over things by saying that, oh, like you can substitute your Java worker with a C++ worker and it all works very well. But like in terms of an API, right, we have a huge space because we have so many operators, so many types, and not everything is implemented. And so one of the big usability enhancements we want to do, especially now since we are seeing many teams come to Prestissimo and start using it. So we're doing something called feature lockdown, where we want to express via like capabilities API, if you will, to the coordinator as to what features are supported in the worker. And I mean, based on the capabilities, we can give early errors based on knowledge, like we don't support some feature or something. And this kind of feature lockdown leads to work that we are going to do in Connect SPI. So hopefully this year we will start work on fenced and unfenced extensibility features for functions and user-defined aggregates, and maybe some work on the actual connector features as well. So far, we've done a lot of work on the Parquet reader, but this year we're also going to focus on Iceberg reader, maybe Iceberg writer. Then there is Presto on Spark, and Meta is kind of working to make this Prestissimo on Spark. And in addition to all that, we're just like constantly building operational experience, running more and more query workloads with Prestissimo. And as a result, you will see a lot of emphasis on stability, a lot of fixes going in the code base. I mean, as of the last month, we saw like a spike in the number of commits to get this to happen. And Meta is also doing like a fancy fuzzer-based testing strategy to kind of make this happen. So last but not least, I want to thank the entire community. We have a big engineering team across Meta, IBM, ByteDance, Intel, who have been contributing to this project. There are links for the GitHub and Slack groups that we have. But this year we also started this Presto native working group, and this meets every 2 weeks on Thursday at 11 a.m. PST. And please feel free to come if you're interested in this project, you want to use it, you want to contribute to it. In this group, like you can present any features, you'll get information about all the new features that we're doing, design issues are discussed, and we just provide more information to everyone who wants to join the community. So once again, thanks especially to the Meta team for this wonderful collaboration. And they're always there to answer our queries and do code reviews and yeah, they kind of spearheaded all this, and we're seeing all this amazing stuff happen. So thanks.